Welcome to Lecture 8. We're going to start where we left off at the end of Lecture 7. I did not get quite as far doing it live in a 50-minute class period as I had done before. But anyway, we looked at periodic trends, we looked at why, and in doing so, we looked at why metals lose and nonmetals gain, why substances bond, and the difference between ionic bonding and covalent bonding in terms of predicting if I have two elements, how do I know what kind of a bond are they going to form? And we are going to continue talking about ionic bonding today. I'll pretty much wrap it up with this lecture. It's pretty easy in terms of the properties are all very predictable because of that strong positive negative electrostatic force between those ions. Very strong attraction, high melting points, high boiling points. If they're melted or dissolved in water, they conduct electricity and so on. All are solids at room temperature because of that strong attraction. What we've got left to go over is more about the formulas, because the ionic compound formula writing is harder than the covalent. But then covalent has something else to deal with, so it all kind of balances out. So why is the formula for calcium chloride CaCl2? Let's review the naming one more time. Metal first in the name and in the formula. Okay. Nonmetal second in the name and in the formula. We drop the ending of the nonmetal and add IDE. So chloride, oxide, bromide, fluoride, nitride, and so on. There aren't that many nonmetals. You will get used to it. So the kind of thinking that we began at the end of Exam 1 material and reinforced in Lecture 7 was to think about each element in terms of, is it a metal or a nonmetal? Calcium is a metal. How many valence electrons does calcium have? It has 2. It's in group 2A. As a reminder, the A groups 1 through 8A are much more predictable than the B groups. So for metals, that means that they will lose the valence electrons they have. So metals in A groups, the numbers that are written at the tops of the columns or the families on the periodic table, followed by an A, are called the main group elements, the S and the P block. Those elements are pretty predictable. The nonmetals are very predictable, but the metals in the A groups, we know they're going to lose the valence electrons they have. So calcium has 2, loses 2 to form a positive 2 ion. Chlorine, nonmetal, has 7 valence electrons, needs to gain to make 8, so it means it gains negative 1 to form a negative 1. Now, this ion has a positive 2 charge, and this ion has a negative 1 charge. Those charges are not balanced. They don't add up to 0. So I need 2 of these negative 1 calciums so that I have a total of a negative 2 charge to balance out that positive 2 charge. In reality, you have a calcium ion with a plus 2 charge. And this, remember, this formula represents the ratio between the cations and the anions. So I have 1 cation to 2 anions, and I need that because of the charges. Focus on these charges. You do not have to write them up here, but it does help students to do so. All right, potassium oxide. Potassium, metal, 1 valence electron, group 1A, loses it to form a plus 1. Oxygen, nonmetal, 6 valence electrons, has to gain 2 to make 8. So it has a negative 2 charge. So we have the opposite situation here. I'm going to need 2 of those plus 1 potassiums to balance out the negative oxygen. So this time I have a ratio of 2 cations to 1 anion. It's going to look basically the same, but it's reversed in terms of which one, in terms of the ratio. So this time I have 2 positive ones instead of 2 negative ones. As in Lecture 7, we we mentioned about the transition metals and the fact that they do not perform like the group A, with the exception of 3. let's remind you of what those three elements, scandium, silver, and zinc in the transition metals, will lose the valence electrons they have. The rest of them, some do, some don't. So this little table right here that you can't read as well in Word, but I will just rewrite some of what you're seeing, reflects the fact that some common ions, some elements don't lose, this is metals we're talking about, to form noble gas-like structures. Iron has 8 valence electrons. It's not going to lose 8 electrons. It's impossible. Well, not impossible, but not going to do it in any kind of normal chemistry environment. So the 3 plus ion, it's also known as the ferric ion, has an electron configuration of 3d5. It's a 5 there. Okay. Copper with the plus 2, copper has 9 valence electrons. So when it loses 2, it ends up with a 3d9 outer shell electron configuration. Zinc is one of the 3, has 2 valence electrons, loses the 2 to form the 3d10, so 10. Silver, another one of the 3, has 1 valence electron and loses it to form a 4d10. So those are pretty predictable, but I think you can understand that because those D's are full, particularly stable. Lead, this one that they're talking about here, forms a has a plus 2 charge, which means that the outside configuration is 6s2, 4f14, 5d10. You see how some, I got this from a website, you see how they don't always write them in the same order. And one of the reasons they do this, they write them this way, and it would have been 6p2 here at the end for the atom of lead, is because those are the ones that get lost. Those are the valence electrons. These are not valence electrons. Anyway, lead forms a plus 2, and you lose the 6p electrons. Lead also forms a plus 4 ion as well. When it forms a plus 4, it ends up being xenon, 4f14, 5d10. Iron forms a plus 2 as well, so its plus 2 ion would be 3d6. So the reason that I'm bringing this up here is to reinforce the fact that these are nothing like noble gas structures. So there's nothing particularly magical about that. These metals here in the middle, the transition metals, and those at the inner transition metals, they're just too far from becoming a noble gas. They just really cannot. They're going to form the ion with whatever they're reacting with that forms the most stable compound. And as I said in lecture 7, it's a balancing act between the energy needed to lose electrons. That's an energy end thing. Okay. To the energy out, energy given off, lowered in energy given off when ionic compound forms. Opposites attract, and so energy is always given off when an ionic compound forms. So you have this cannot be larger than this. If so, then the compound will not form. So metals lose the amount of valence electrons that enable this process to occur. So if you were given the idea in high school that everyone wants to be a noble gas, try to let go of that idea. Okay. All right. So just reinforcing here what I was just talking about. All right, what determines the charge on an ion? Well, that coming together and lowering in energy is dependent upon two things. It is dependent upon charge and size, and that is mentioned right here. Difference is how strong the ionic bond is depends on how many charges are on the ions and the sizes of the ions. Okay, so if you have, let's say, lithium fluoride, okay, lithium fluoride versus calcium oxide. Now this is a +1 -1, and it's fairly small, but this is a +2 -2. This charge is going to give these oxides, are, especially with group 2, where you get a +2 and a -2, don't dissolve in water very well, which means the ions will not come apart. So this is much stronger than a +1 -1. And a +3 -3 would be even stronger, and so on. So it's charge first, then size. So if I were comparing rubidium iodide to sodium chloride, the rubidium and iodide ions are bigger. So the attraction, they can't get as close together, is less than it is for the smaller sodium chloride. And of course, lithium fluoride would be even stronger because that would be smaller. I am referring to our trends for size on the periodic table. Okay, so how strong the ionic bond is depends on, and of course that how strong the ionic bond is that amount of energy that is given off when the compound forms. In lecture 7, we looked at what these compounds look like in the solid state, okay, and talked about the giant ionic structure, and we talked about ionization energy. I think we're going to talk about what being brittle means and why they dissolve in water. And then I think we were about ready to do some examples and work on those formulas. Yes. Okay. So what is they're brittle. You can take a piece of rock salt and a butter knife and break the rock salt into pieces. And the reason why is when you put stress on that solid crystal, you can actually move a layer of these ions such that the positives are next to the positives and the negatives are next to the negatives, and they repel one another. So it actually repels itself to pieces. Many ionic compounds dissolve in water, not all. If the ionic bond is particularly strong, then it will not dissolve in water, like the oxides and so on. But sodium chloride salt has seems like an almost infinite amount can be dissolved, but there is a limit. Why do so many of these ionic solids dissolve in water? Well, the secret is water. Water is a molecular compound, as we mentioned before, and as we will learn as we get into lecture 10, 9, 10, the oxygen-hydrogen bond, because of the electronegativity difference, which we talked about in lecture 7, is not equal. Oxygen has a stronger electronegativity, a higher electronegativity than hydrogen does. The difference between them is not large enough for this bond to be ionic, but it is unequal, which means that it's polar covalent. Oxygen gets a little negative, pulling on those electrons. Hydrogen gets a little positive. So each of these hydrogens, because of the shape of the water molecule, this end of the molecule is positive. This end of the molecule is negative. It's a polar substance. So when I put a salt into water, I'm going to show you a video as to what happens, because this will come up in the next set of material. So let me go to, okay. Ah, this is it.
Let's add a small amount of table salt, sodium chloride, to water. As you know, sodium chloride dissolves in water. Click on the zoom button to view sodium chloride dissolving in water on a microscopic scale. Polar water molecules interact with the positive and negative ions of a salt. The positive ends of the water molecules are attracted to the negative chloride ions. The negative ends of the water molecules are attracted to the positive sodium ions. This interaction between water and the salt ions causes a salt to break apart or dissolve in water.
Okay, we'll look at this animation again when we start talking about chemical reactions, but isn't it kind of amazing that an ionic solid, like this one, that has such strong attraction between the positive and negative ions can actually be taken apart by water? The interaction of the water molecule with those ions lowers the situation in, lowers the system in energy. And even though it takes energy to pull this ionic solid apart, the reason it happens is because the interactions that are formed with the water molecules lower it in energy more than the energy you're having to put in to tear the ionic solid apart. So I just wanted to show you that so you'd have a picture in your mind. We're going to come back to that later in the course. All right, so that's how they're soluble in water. They do not conduct electricity unless they are dissolved in water or they have been melted. You must have moving charges in order to in order to conduct electricity. All right, little naming here and reminder about charges from the different groups. Now, when we get to, we're going to talk today about the transition metals and how we're going to deal with that. And we are going to deal with it by using Roman numerals, which I got to right at the end of lecture 7. So we're going to use capital Roman numerals, so you'll get to practice that, to show what the charge is on those transition metals, and that'll be in the name. So like iron to chloride, these are actually easier because you don't have to predict what iron is going to do. You just have to look up the symbol and know that it's a metal, so it's +2. This is the charge. It is not how many are in the molecule. Okay? And then you have to look at the nonmetal. Okay? Chlorine forms a -1, so that's how we're going to deal with the transition metals. I'm going to skip polyatomic ions for now. We're going to do some examples and then we'll come back to those. I'll do the single atom ions or monatomic ions first. Okay, and then we'll come back to those. All right, so group A here on our practice is exactly that. It is monatomic, meaning just one element. All right, one element of a metal, one element that's a metal, one element that's a nonmetal, and so on. And we're going to work through these, okay? So I hope you have your periodic tables out. We're going to name them and write their formulas. So I'm going to go as slow as I can, but not going to put those pauses in. So if you want to pause it at any time and give these a try and then come back, then please do so because that's the kind of practice you need. All right, sodium, metal, 1 valence electron forms a +1. Sulfur, nonmetal, 6 valence electrons, gains 2 to form a -2. I therefore need 2 of those +1s to cancel out the -2, and the name is sodium sulfide. Leave the metal name alone, change the ending of the nonmetal. All right, calcium, metal, 2 valence electrons, forms a +2. Bromine, 7, gains 1. So I need 2 of those negative ones to cancel out the positive 2, and my name is calcium bromide. All right. Potassium and oxygen, we've already done that one today. Potassium, metal, positive 1 because of the 1 valence electron. Oxygen, 6 valence electrons minus 2 to gain 2. So I need 2 of those potassiums, potassium oxide. Now, notice that when we have a metal present, we are not going to use prefixes like we're going to do when we do covalent compounds. So there is no di, tri, tetra, any of that with metal, nonmetal compounds. All right, magnesium and nitrogen. Magnesium, 2 valence electrons, loses them, metal. Nitrogen has 5, nonmetal, so gains 3. This is the first time we've had a 2-3 situation. I've got to make both sides the same value. So I need a common factor between 2 and 3, and that would be 6. So 3 times the positive 2, 2 times the negative 3. How many ions altogether do I have in this compound? 3 plus 2 is 5. 3 to 2 ratio between cations and anions. The name, magnesium nitride. Okay. Hydrogen and fluorine. You will see it again when we talk about covalent compounds. So this one is almost ionic. It's very polar, but we're going to go ahead and just leave it where it is. Hydrogen, in terms of being here in the set of ionic compounds. Now, hydrogen is a different element. Most abundant in the universe, but behaves like a metal and a nonmetal. It is placed in group 1 because it acts like group 1 elements, even though it's not really a metal. So hydrogen forms a +1. Fluorine, the big dog on the table in terms of electronegativity, and it forms a -1 because it has 7 valence electrons. The name is going to be hydrogen fluoride. Ignore the cat. I am. All right, strontium, metal, 2 valence electrons, +2. Sulfur, 6 valence electrons, nonmetal, so gains 2. Strontium sulfide is the name of our compound, and I did not need to add subscripts because the +2 and the -2 canceled each other out. All right, hydrogen and selenium. Hydrogen, +1, selenium, same group as oxygen and sulfur, 6 valence electrons, so it forms a -2. So I need 2 of those +1s, and my name is hydrogen selenide. Now, when we get to the covalent compounds, and you have things like, when you have 2, technically, in number 5 here, we really do have 2 nonmetals, even though hydrogen acts like a metal most of the time. It is, how do you know which one to put first? It is the one that is to the left on the periodic table, and that is why hydrogen is written first in these compounds. All right, sodium, metal, 1 valence electron, forms +1, phosphorus, nonmetal, 5 valence electrons, forms a -3. So I have a -3 on this side. I need to make this side +3, so I'm going to put a little 3 there. Sodium phosphide. So in these practice problems, you are seeing pretty much all of the different nonmetal endings. I mean, how to drop the names, the ends of the names, and add the IDE. All right. Aluminum. Don't forget, it is a metal. Many students want to make it a nonmetal and gain 5. It is in group 3A. It is on the left of the staircase. It has 3 valence electrons. It loses them to form a +3. Oxygen, 6 valence electrons, nonmetal, forms a -2. So a 3-2 situation. So I'm going to make both sides 6. And this is aluminum oxide. Okay, gallium, same group as aluminum. It is a metal. It's a metal that actually will melt in your hand. It's got such a low melting point. 3 valence electrons, loses them, positive 3. Iodine, nonmetal, group 7, 7 valence electrons, gains 1 to make 8. So I need 3 of those negative 1s to cancel out the positive 3, and it's gallium iodide. All right, scrolling. Do group B. Now in group B, we have the Roman numerals for our transition metals. So remember, it is the charge on the metal. So we're going to call this iron. Well, the name is going to be iron. 2, I put the Roman numeral in the name, but not in the formula, chloride. All right, so the only thing that changes here is in the name, I insert that Roman numeral. That Roman numeral tells me that iron is a +2. Makes it easy. Chlorine, nonmetal, group 7, gains 1 to make 8. So I need 2 of those chlorines to cancel out the positive 2. Cobalt, positive 3. That's what the Roman numeral tells me. Oxygen, negative 2. 3-2 situation, right? 2 cations to 3 anions, and the name is cobalt 3 oxide. Okay. Nickel, positive 2. Sulfur, 6 valence electrons, negative 2, so they're good as is. And this is nickel 2 sulfide. All right. Gold, positive 1. Phosphorus, group 5, gains 3 to make 8. 3 positive 1s to cancel out that negative 3. So this is a ratio of 3 cations to 1 anion, 4 ions altogether, and the name is gold 1. Oops. Have you noticed my little pen features working better? Phosphide. I'm not having to pull up the control panel to get my pen back and so on. This program is very unpredictable. All right, next one, cadmium. +2. Iodine, group 7, negative 1. So I need 2 of those negative 1s to cancel out that +2. Cadmium 2 iodide. Okay. Platinum with a +2. That's what the Roman numeral tells me. Nitrogen, nonmetal, group 5, gains 3 to make 8. It has 5 valence electrons. So negative 3. 3-2 situation again. Make both sides 6. So 5 ions altogether. Platinum 2 nitride. Zirconium, Zr. That Roman numeral tells me it's a +4. Oxygen, 6 valence electrons, negative 2, gaining 2 to make 8. I need 2 of those negative 2s to make this side negative 4 to balance out the positive 4 on this side, and this is zirconium 4 oxide. This is the one we did in lecture 7. Molybdenum, +4. Sulfur, same group as oxygen, so it has a negative 2. Same type of compound formula. Molybdenum I think I left the Y out. Denum sulfide. Oh, Roman numeral. Got to put the Roman numeral in the name. Molybdenum, and the reason why is molybdenum, zirconium, platinum, cadmium, many of these transition metals form more than one ion. So there may very well be a molybdenum 2 sulfide as well. So I have to tell you in the name which one we're talking about. All right, osmium, +2. That's what the Roman numeral tells me. Fluorine, group 7, gains 1. So I need a little 2 by the fluorine, osmium, 2, fluoride. Okay, one last one, rhodium, RH, with a +3. Selenium, non-metal, group 6, gains 2. So I need a 2 over here to make it 6 and a 3 here to make it 6. So this is rhodium, 3. I'm going to run out of room. Selenide. Right, group B done. All right, we're about ready to talk about polyatomic ions. So exciting. And there that is. Groups C has some polyatomic ions in it. So let's scroll back up to where that was discussed. And I believe I have a link in here. I hope I have a link in here. Yes, I do. Of polyatomic ions. Okay, polyatomic ions are basically, I call them packages. They are basically covalent compounds with a charge. So they are covalently bonded. Unless you are told otherwise, they pretty much stay together as a package. So it's like a molecule with a charge. So it's not just one ion like we've been dealing with, but the way we're going to put them together is exactly the same way. Okay? So there is one positive polyatomic ion, and that is ammonium. All right? So let's do an example right here before we talk any further. Ammonium chloride, common compound. Now, this is what's really confuses students. The formula for ammonium is NH4. That 4 there confuses students. They think it has something to do with the charge. It just does confuse them. That is just the formula for NH4. It's the charge, however, just like I've been doing, that I'm going to focus on in order to put this thing together. So +1, chlorine, group 7, nonmetal, -1. I need 1 ammonium for every 1 chlorine. There are 2 ions here. 1 cation, 1 anion. This is a package. Just a polyatomic ion. There are many others. Many of the ones I want you to know are here in this little paragraph. So sulfate, you need to memorize these. Charge, formula, and name. Nitrate, carbonate, hydroxide, phosphate. So you've heard these words before. Permanganate. We're going to go to a table, though, here that's linked in the notes, to show you some of the other polyatomic ions. And they're organized on this table by charge. So at the top of the table, there are the +1 ones. And we're not really going to, we will get to the hydronium ion later in the course when we talk about acids. But right now, we're really not going to be dealing with it. So you do need to know ammonium. Next is the -1 anions, and there are quite a few. The ones you need to know are hydroxide and nitrate. Those will come up again and again and again. Hydroxide and nitrate. And let's add permanganate to the list because it comes up pretty often. All right, so permanganate. A manganese ion in the middle surrounded by 4 oxygens. The whole thing has a -1 charge. So we're going to use, we'll write the formula, we'll focus on the charge for putting it together. The most common compound for permanganate is potassium permanganate. So as you see, most of these polyatomic ions are negative. So they'll go second in the formula and second in the name. And the naming is easy. You just say the name of the ion, of the polyatomic ion. So potassium permanganate. There's your K. Its charge is +1, group 1, metal. And then you write down the formula for permanganate. There you go, done. And now focus on this charge. I got a -1 and a +1. That's what I'm going to use to put this thing together. I need one of each. We generally do not use the parentheses when I need one. It wouldn't be incorrect, but we generally don't. All right? So 1 potassium, 1 permanganate, 2 ions. 1 cation, 1 anion. Okay? Moving on to the -2 charged ions. Carbonate, very common ion in our waters. Chromate comes up quite a bit in the course. Sulfate, another very common ion. Notice I'm not putting stars by all of them. And then you have your 1, -3, which is phosphate, and that one does come up quite a bit as well. So this table is linked in the notes. You can go and look at them if you want to see how they're put together, but they are essentially a molecule with a charge. We're going to focus on the charge, just like we've been doing, to put these compounds together. There really isn't any difference other than you're dealing with more than 2 elements. And that's how you know you have a polyatomic ion when you see, so this is 2 elements right here. This is what I'm talking about. This is 2 elements, okay? So no polyatomic ion. Magnesium oxide. Now, what do you do when you have a transition metal like this one and you have to name it? Well, you look to the right. Look at what it's with. Sulfur. What is sulfur's charge? It's -2, and I have one of them. So iron must be +2. So you're figuring out the charge on the transition metal because you have to include it in the name. So this is iron, Roman numeral 2, and that's for the charge on the iron, sulfide. So you figure out the charges from looking at the negative side first, and then put that charge in the name. All right. But anyway, those are two monatomic ion compounds. Just one, no polyatomics. Same thing for the next few. Now you get here with ionic compounds containing polyatomic ions. How do you know it's a polyatomic ion? Because I see 3 elements here. 3 elements, 3 elements. Many of them contain oxygen. 1, 2, 3, 4 elements here. This is actually a combination of 2 polyatomic ions. So let's talk about that one for a minute. Ammonium. Let's write down the formula for ammonium, NH4. Focus on the +1, however, when you start to put it together with phosphate. Formula for phosphate, PO4. It has a -3 charge. Now forget about the 4s. You are done with them. Focus on these charges. +1, -3. Got to make this side the same as this. I've got to make it +3. The way that I do that with polyatomic ions, I put in the parentheses and I put a little 3 on the outside. We've talked about what that means previously in the course. It means you got 12 hydrogens and 3 nitrogens, but it really means also that I have 3 +1s to cancel out that -3. Ammonium phosphate. You don't have to change anything when you're dealing with polyatomic ions. All right, so let's go back to C and let's do some practice problems, and then we'll move on into covalent compounds to finish this up for lecture 8. All right, so all of these involve polyatomic ions, so you might want to make a list of those, pause the video so that you I think there's a table of polyatomic ions in the inside of the front cover of your book, or copy it down on a sheet of paper of the formulas, charges, and names. All right, calcium, just regular old calcium, positive 2. Nitrate, formula is NO3, and it has a negative 1 charge. I need to make both sides the same, so I need 2 of those negative ones, so I'm going to use the parentheses and put the 2 on the outside. Calcium nitrate. Okay? Sodium with phosphate, very common. You can use it as a cleaner. You can buy it at the store as a cleaner. It's a heavy-duty cleaner. Sodium plus 1, phosphate, written the formula, done, forget about the 4. It has a negative 3 charge. That's what I'm going to focus on. So now I have a negative 3 on this side and a positive 1 on this side. I need 3 of those positive ones to cancel out the negative 3. Sodium phosphate. Ammonium and hydroxide are 2 polyatomic ions. Ammonium. All right, you've written the formula, forget the 4. Focus on the positive 1. Hydroxide, OH, with a -1 charge. Students have difficulty with hydroxide because there's no subscripts, so they don't recognize it as a polyatomic ion, but it is. It is more than 1 atom. Anyway, you got a positive 1 and a negative 1, so they cancel each other out, so you're good the way you are. Ammonium hydroxide. Okay? Iron 3 nitrate. So iron has a +3. Write the formula for nitrate, NO3, but focus on the charge. +3, -1. I need 3 of those negative ones to cancel out the positive 3. So this is iron 3 nitrate. And remember that Roman numeral is the charge on the metal. Nickel 2 sulfate. Nickel has a +2. That's what the Roman numeral tells me. Formula for sulfate, SO4. But it's the -2 charge I'm going to focus on. -2 plus 2, so 1 of each is good. And this compound is nickel 2 sulfate. All right? Potassium and carbonate. Potassium +1. Carbonate, formula is CO3. Focus on its -2 charge to put this together. Potassium, I need 2 of those +1s to cancel out that -2. Potassium carbonate. Potassium is not a transition metal, so I don't need to put a Roman numeral in. Cobalt is a transition metal, so that's why the 2 is there. So that means it's a +2. Formula for phosphate, PO4, -3 charge. Focus on these charges. Make them both 6. So I've got to put a parentheses around the phosphate. Looks complicated, doesn't it? Cobalt 2 phosphate. Okay. Copper 1 hydroxide. Copper with a +1. Hydroxide, OH with a -1. So those are good, +1, -1. Copper 1 hydroxide. Okay. Vanadium with a +2. Nitrite. There's 1 less oxygen than nitrate, but still has a -1 charge like nitrate. So I have a +2, -1. I need 2 of those -1s to cancel out that +2. Vanadium 2 nitrite. Okay. I don't believe this oxalate ion was in that table of polyatomic ions, but I could have missed it. Okay, I'm going to have to give myself a little room. So I'm going to have to scroll. All right. Barium, plus 2, group 2, metal. Oxalate, the formula is C2O4 with a minus 2 charge. Focus on those charges, plus 2, minus 2, so we're good. Barium, not a transition metal, so no Roman numeral, barium oxalate. All right, that wraps up our examples. What I'd like to do for our last 15 minutes or so is get you kind of started on thinking about covalent compounds. And in particular, what I'd like you to do is stop the video, and if you have an index card at home, I will try to remember to give some out in class. I want you to get a regular 3x5 index card because you're going to be copying down some steps onto that index card for doing Lewis dot structures. So let's go ahead and scroll and start talking about a couple of things, and then we're going to just get started on Lewis dot structures, which is the thing that makes covalent compounds a little different. One thing I'd like to talk about first, though, is the law of constant proportion. It seems like we've already, really covered that because it says that Joseph Proust was the guy who came up with it, states that elements combine in fixed proportions. Well, this really seems like a restatement of that compounds have fixed mass percentages. The idea is that the ratio of masses is the same no matter what size the sample is. So I've got a little practice problem for you here. 2 samples of carbon tetrachloride were decomposed in their constituent elements. One sample produced 32.4 grams of carbon and 373 grams of chlorine, and the other sample produced 12.3 grams of carbon and 112. So do you have the same percentages of the elements? Well, if we just talk about carbon, okay, then the percent of carbon in the first one would be 32.4 over 32.4 plus 373. So let's see what we get when we do that, times 100. Okay, the second one would be 12.3 over 12.3 plus 112 times 100. So let's see what we get when we do that. Okay, I get 405.4 for the total on that first one. So my percentage on the first one is 8%, 7.99. So 8% carbon on this one. On this other one, I get for a total 124.3. And the percentage is not going to be the same. The percentage on this second one is 9.9%. So this is not consistent with the law because I should get the same percent of carbon, and I just did carbon. We could do chlorine as well, but just thought I'd check the carbon first. So 9.9% carbon for the second one. So this is not consistent with the law of constant proportion. All right, this is important as we get into covalent bonding. There are elements that actually exist as molecules. We have been talking about elements for a while, and for most of them, all of the metals, which you know are a large proportion of the elements, they are atomic, meaning that they exist as single atoms. But there are 7 diatomic elements, 2 atom molecules. And we can call them molecules now because they're made up of nonmetals. So we are doing nonmetals when we are talking about covalent compounds. Yes, you can get a metal and a nonmetal to form a covalent-like compound because the electronegativity difference isn't large enough. But for the most part, your covalent compounds are nonmetal. There are 7 elements that do not come as atoms, and you need to know what they are. I always tell students it's like 7 in the shape of a 7. So let me go to that periodic table that we've used so much. No, that's not what I wanted to know. There we go, this one. All right, so this is what I'm talking about. 7 in the shape of a 7. So hydrogen, the weird element, can sometimes be, you'll see it on periodic tables, placed right, hold on, let me get the pen back, placed right here, okay, hydrogen, all right, because sometimes it forms a -1. Anyway, the 7 elements that come in as diatomic elements are like all together like this. So I always tell students it's like a script 7, starting with nitrogen, oxygen, hydrogen, fluorine, chlorine, bromine, and iodine. Those elements, when they when you are talking about the element, they exist as diatomics, H2, N2, F2, and so on. Okay? You need to know that. All right. All right. Scrolling. So now we're going to talk about covalent bonding, where instead of gaining and losing, we're going to share to complete our outside shells. Remember, we've talked about before that the nonmetals are always going to complete their outside shells. Well, instead of gaining and losing, we are going to share. We can talk about these substances as being true molecules. Okay, they are molecular. There are some that are not, but we'll talk a little bit about that at the beginning of the exam 3 material. There are no full charges, but we certainly can have partial charges. We've talked about polar a little bit. We are going to use the Lewis dot structure to help us characterize covalent compounds. So the naming and so on and formula writing for covalent compounds is quite easy, but you have to deal with Lewis dots. Now, for some reason, this did not come over into Word, but what was here was you can 1, 2, 3, 4, 5, 6, 7, 8. We can think about a row on the periodic table, either the first, second, or third row, and talk about the numbers of valence electrons as dots. We've talked about that before. So hydrogen has 1 valence electron. Helium has 2. Really rather do a different row rather than the first one because it only has 2 elements, so let's change that. Let's talk about second row, okay? So lithium has 1 valence electron. Beryllium has 2. And remember I told you before that they're 1 on each side, and then we start pairing them up. Boron has 3. And so on. That's what was in these boxes. Carbon has 4. Now, having done this, when we start doing the Lewis dots for compounds, I do not want you to micromanage whose or whose. I am just presenting the idea that valence electrons are dots. All right, I had to pause the video, so I hope that I can't remember exactly what I was saying when I stopped, but we were putting the valence electrons around these elements. And I believe I was in the process of saying that when we put these elements into compounds, we are going to use these numbers of valence electrons, but we are not going to micromanage whose electrons are whose. 6 for oxygen. Okay. And then fluorine has 7. So we're going to count them. We're going to use dots to signify where electrons are. And then neon would have 8. But we are not going to start off by putting fluorine 7 around it or oxygen 6 around it. You'll see how we're going to do this. That's the reason we need the index card. So down here in this box, it is an example of how we're going to use the valence electrons to signify bonding covalently. So there's 2 ways we could do that. We could, when I talk about the hydrogen molecule, which is the element hydrogen, I can put the 2 dots that come from the 2 hydrogen atoms in between this way, or I can show it with a dash. We're going to use the dashes for bonding. So 1 dash is a single covalent bond, and it signifies sharing 2 electrons. One electron coming from one atom, one electron coming from the other. But we're not going to micromanage whose or whose. What was here, and just did not come through in the word, was oxygen molecule. And that in this molecule, the oxygen atoms actually share 4 in a double bond, and then the other electrons that are present in the molecule are shown on the outside. Well, it's kind of hard looking at this if you use the dots for bonds to know which are bonds and which are not bonded electrons. So the better way to draw it would be with 2 double lines to show the sharing of 4. So a double line is a double bond, and you're sharing 4. Sharing 2 with a single, sharing 4 with a double, and then a triple is sharing 6. And we really don't go any higher than that. There are very few elements that do the double or triple bonding at all. Then coming back to this oxygen molecule, the extra electrons that are present, because remember each oxygen did have 6, so I have a total of 12, are shown as lone pairs. That's what these little dots that aren't in dashes are called. They're not involved in bonding. So this is the deal. You want to make sure what these nonmetals are doing is they're sharing to complete their shells. Just like they gain to make 8, they are sharing to make 8. So in this oxygen molecule, 2, 4, 6, 8, this oxygen is tricking itself, so to speak, into thinking it has 8 around it. So what you want to do in this endeavor we're about to start is give everyone 8. Hydrogen is an exception, fine with 2, okay with 2. So there's the 2 right there. For all the others, there's another exception, but anyway, for all the others, give them all 8, but you have to satisfy the fact that oxygen, 2 oxygens, gives you a total of 12 electrons. So I'm trying to give you the big picture here. So 2, 4, 6, 8, 10, 12, I have my total, and each oxygen has the 8 at once. And you'll hear me probably talk about them being happy because they've got their octet of electrons, and you have used all the valence electrons that were available. So that's kind of the big picture of where we're headed. Drawing these diagrams is going to enable us to make a lot of predictions about properties, shapes, and so on. So this is what I want you to do with the, I'm going to decrease the size of this a little bit. I want you to take that index card, and I want you to take these steps that are here, and we're going to put these on the front of the index card. So this is step number 1, step number 2, 3, 4, 5, and 6. 6 steps. Write small. Stop the video, leave it, leave the screen showing this, and copy this material onto your index card. You are going to be able to use that index card for your next exam. The back is for some other information. What I'd like to do in the rest of the time that we have, there goes the dog again, and the rest of the time that we have for this video is get you started just doing a couple of these molecules. Then we will finish those up at the beginning of lecture 9. Okay. And I want to talk about naming because it's so very easy, and I just want to go ahead and take care of that. Okay. So let's take our steps and let's apply it to just the first 2 elements that are here. The first 2 compounds, sorry. All right. So using the steps that are on the card. So step number 1, add up the valence electrons. Okay. So CH4 is my example. All right. Carbon has 4 valence electrons. Each hydrogen has 1, but I have 4 of them, so I have a total of 8. She thinks it's time to eat. It's not. All right, the element to the left, which is generally the one that you have the fewest of, is going to go in the middle. We are going to do very simple examples where one atom goes in the middle and it is surrounded by the others. Okay? Now, second step, connect atoms with bonding dashes. So we're just going to go ahead and connect those 4 hydrogens to that carbon with bonds, single bonds. Okay? Step number 3, give each atom 8, except for hydrogen, which we've also talked about, and boron. Boron is okay with 6, and hydrogen is okay with 2. Lithium and beryllium are exceptions as well, but they're metals, and personally I don't do Lewis dot structures for ionic compounds. Okay, so we've done that. We've done step 2, and we've given carbon has 8, 2, 4, 6, 8. Hydrogen is fine with the 2. Now this step number 4 is a check step. 2, 4, 6, 8. That is the total number of valence electrons we had, and we are finished because everyone is happy. All right? We will not use steps 5 and 6 until we get into lecture 9. All right, let's do the same thing for NH3. Otherwise, before we leave CH4, let's review the names and name both of these examples as we do them. So covalent compounds are easy because you use prefixes to tell how many atoms are in a compound. So if I have something like CH4, if the element that's in the first position, first of all, is usually the one on the left, to the left on the periodic table, and if I only have one of them, I don't say monocarbon. Generally, I just say carbon. Carbon, our prefix for 4 is tetra, tetra, and then I do the same thing with the second element I did before. I drop the ending and add the IDE. So carbon tetrahydride. All right? We're getting ready to do NH3. So again, I only have one in the first position. So nitrogen, tri for 3, hydride. Right? I've got a couple more examples below here. So what if I don't have one in the first position, like in this one? Then I use the prefixes for both. So P2 becomes diphosphorus, not changing the name of the first element, and then 5 pentoxide. All right? Carbon, CO. Carbon, I don't say mono, I just say carbon, but if you have one in the second position, you do use the mono prefix. So carbon monoxide. Okay? Carbon tetra for 4, it's hard to see, 4, carbon tetrafluoride. All right? So naming these is super easy. So writing the formulas is super easy, much easier than ionic, but you got this whole Lewis dot thing to deal with. All right, let's do the Lewis dot for NH3, and then we're going to call it a day. Okay. So, NH3, add up your valence electrons. Nitrogen has 5, each hydrogen has 1, I have 3 of them, so again we have a total of 8. Connect with dashes. Put nitrogen in the middle, it's to the left. I have 1 nitrogen. Okay? Give everyone 8, it's third step. Each of these hydrogens is fine with the 2 it has around it. Nitrogen, however, only has 6. 2, 4, 6. So I am going to give it a lone pair to give it a total of 8. All right? And now, step 4, count your electrons. 2, 4, 6, 8. We are good. This is the Lewis dot structure for NH3, nitrogen trihydride, or the common name is ammonia. Let's do one more. HF. Now let's skip HF because it has 8 as well. Let's do OF2. Okay? All right. So count your valence electrons. 6 plus 2 times 7, 14, and 6 is 20. We'll do HF at the beginning of lecture 9. All right, so oxygen to the left, you only have one, put it in the middle. Connect with a single bonds, bonding dashes. Now give everyone 8. This oxygen right now thinks it has 4, 2, 4. So we're going to give it 2 sets of lone pairs, okay? So it has 8. Now this is what students, I don't know why students do it, but they want to put dots by themselves. There's an even number here on the majority, the vast majority of compounds have an even number of valence electrons. Nature does not like electrons to not be paired. Those compounds tend to be very reactive. They're called free radicals, and they are often cancer causing. So most compounds have an even number of valence electrons. Put them in as pairs. All right, before I added that dot, this fluorine thought it only had 2 with a dash. So it needs 6 more electrons to give it a total of 8. Now remember, we are not micromanaging whose electrons are whose. It's really the way it exists in a molecule. The electrons are actually much more mobile than we are letting on. And it's like they're in a pool and you're using them to construct the molecule. All right, so this fluorine also needs 6 more, so it has a total of 8. All right, so we have given everyone 8, and now step 4, we're going to check to see if we have our 20. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We do. This is the Lewis dot structure for oxygen difluoride. And we will finish these examples with lecture 9 and get into shapes of molecules.